So I'm Jeff Burke from UCLA, and I give the update for application research for ICEAR. Given some other discussions that we've had, I'm going to try to use this as a way to make some progress towards how we might, from the application point of view, evaluate NBN versus TCP/IP for AR and mixed reality. So this is a little bit of conceptual material, and then along the way I'll update in terms of what we're doing for applications, and then end with some plans for next year. Not in this talk are really deep conversations about app requirements driving the other research. I think that shows up in the other discussions. Revisiting app concept material that we've talked about before, and our current sorrows regarding how hard it is to do some of these demonstration apps, so I'll try to avoid complaining about that. So if you recall, the ICEAR proposal is looking at AR as an extension to the web, and an exchange of context from a user device that is sharing its context, which could be the point of view camera, or better even, information coming from one of these FPGA accelerated ML processes that are analyzing that video and just providing features as context. And then services, I'm a little kind of agree with Dave, I don't necessarily like the word services, but services are providing content in response to that context in this flow that is like the web is today. We share bits of information about as we browse and get content in return. So this looks at this loop happening faster and with more granular content. And we focus a lot on video in the discussion, but that's because video is sort of the beginning of a lot of the AR context, as well as a common type of content. But you could imagine these, this data being from other types of sensors. So with this vision of AR as a web of decentralized content, part of what we're struggling with is the question that we've gotten, which is, well, compare it to how TCP/IP does for this. And this way of thinking about AR doesn't exist, and comes in part from an ICN way of thinking about the world. So we're struggling with how do we make comparisons with TCP/IP. And I won't answer that completely in the talk, but we'll get to it a little bit. So over the last year, we've done 2 additional integration tests or experiments that involve building both around IP and NBN, some AR and MR examples. And I'm not going to go through this table in detail. It's 2 slides. You'll get the PDF at some point. But I'll touch on what these experiments are. So if you recall, in the first year, we did an AR demo that was basically about a loop where we capture video on a mobile device, process it in a couple of different edge processes that sit somewhere close to where that device is, publish the annotations that are generated from those processes, things like pose information that Jason mentioned, publish that back to the AR device, and just label the world. That was the loop of the 2017 prototype. In 2018, 2019, we did 2 kind of larger scale integrations, which I'm going to talk about now, and then you can refer to the table after the talk just to see how they might lead up to our overall objectives. So one of these was an AR, and both of these case studies kind of borrowed from this Intel NSF project, but also are big parts of other work that we're doing. So they're not entirely around the ICN question. In fact, this one not necessarily at all. So this was a 45-minute immersive AR experience that was done at UCLA with an audiences of about 10 people at a time, built by about 30 students. And the basic idea was an immersive theater experience. And that's all I'm going to tell you. You can watch the video if you want to learn more. And the way that we conceived of this experience was there were about 14 or so client devices that were used, that had a shared AR and VR world, so a virtual world. And you might be looking through a mobile device and get some elements from that virtual world overlaid on the physical world. There might be a projection on the wall that was coming from a laptop or a workstation that was a picture of that virtual world as well. And so this was a shared AR and VR world, and we had to have networking to communicate between each of these devices and sync up what was going on in the world. And this doesn't have edge processing in the same way that we talked about it here. But what we learned a lot about deploying networking in this LAN environment. And just a couple of takeaways. The LAN versus cloud divide in the IP world, whether you think that it's actually there or not, in practice adds a significant complexity. We tried to do everything in the LAN, which meant the cloud-based tools kind of didn't know what to do. And then, of course, when we needed to get content out of our LAN or get logs or data out of the LAN, we had to figure out then what is the endpoint that we're connecting to in the cloud, where does the data go, and so on. These were sort of different worlds. We also learned that we couldn't focus just on development. And so when the word deployment came up in the panel, I was very excited. This is a lot of the effort in putting even this simple example together, simple in the networking sense, had to do with configuring IP addresses and subnets on the devices, trying to make sure where data goes and where it stays in terms of just providing a security perimeter, and lots of things that were just about configuring the network, getting code and content to and from a bunch of individual devices. And so a little more focus on deployment, I think, would go a long way for being able to do this type of project over in India. I won't go through all the bullets, but also that we didn't really find a good networking framework to efficiently pass messages between all the individual mobile and workstation environments, because the best tools are cloud, kind of assume the availability of the cloud. And so NDN would have done well here if we could have had something, a chunk of it that was easy to deploy and could have replaced the messaging framework that we were doing underneath this case study. So I don't have time in this talk to go into the details. You'll have the link to the video that will tell you about what the project was, and then I'd be happy to go into the networking later on. So about 6 months after that, we were ready to take a slice of that experience, plus what we had been working on in the ICN-WEN project, and use NDN as video transport for a mixed reality experiment that was much closer to our original AR design and had similar sort of constraints. We had a large group of people, many nodes, processing video, and we decided to run it over NDN. So let me describe just briefly what this project was. So if you remember this diagram, or maybe a previous, maybe a version of it was in Jason's talk, and it was in some of our original summaries. We have an AR application proposed in ICEAR that's running on a mobile device, publishes video. It's consumed by a bunch of services. Those services that are potentially accelerated, those services return annotations on that video that are consumed again at the edge device. And so this basic architecture of edge acceleration was applied in a context where instead of the AR device, we were using a higher resolution wireless camera that delivered the data to a workstation, published it as NDN content over layer 2, consumed it in these edge services, applied the annotations, and then made new video streams available with those annotations available. And so the distinction here is we sort of set aside looking at mobile devices for a bit and focused on getting NDN over layer 2 working well for video, at least as well as we could get it. And so, and took one sort of major step forward for our thinking about video, which was to try to align the way that we worked with live content with historical content. So that really the only difference of whether something was in a repo or was coming immediately from a frame acquisition device was just the name component that referred to time. This was a big change in the underlying code, but very consistent with how we'd like to work with video in a data-centric sense. So just quickly, I'll describe the system from left to right. We're inspired by Christian's use of the word worm for the way that the network might store data in this particular context. So we acquire 1080p video at a point of view camera, maybe some other wearable data close to the camera, receive it at a workstation, publish it as NDN data, consume it in a number of Docker containerized ML processes that did object recognition, face recognition, and another set of object recognition called props. So we were not using the accelerated OpenPose yet. It wasn't ready at the speed that we needed, but it would get slotted into the dotted line props there. Each of these and the original video is published as NDN content, and then we created a faster implementation of the repo, or of a repo, persistent storage, that consumes all the annotations, consumes the raw video, stores it, and then makes all of those things available as NDN data. This had some impacts on how we chose to name the source video, how the annotations are named to cross-reference with the video frames that they refer to. And then afterwards, we also have some processes that operate on both the annotations and the raw video that include dividing that video up into segments based on semantics. So if you imagine these things on the left are doing semantic tagging more or less at a frame level of what's in the scene, there are some processes on the right that are watching changes in those semantics and trying to decide when the video changes in terms of what's going on in it. And those are published back as NDN content, again, consumed and stored by the repo. And then eventually, video and some other things are retrieved and projected out into the world from a couple of other processes here. And so in the middle is both the network and storage. And so one of the nice sort of confirmations was starting to think about a much more sort of closely, coupled isn't the right word, but co-designed way of thinking about storage and networking worked really well for this particular application. And to Dave's point earlier about, instead of thinking of things as big services, these are really fairly granular functional blocks that are all publishing and consuming from the network, which is also stored. And I describe what these labels are, but just quickly, the red shows where we would take advantage of the cross-layer optimizations that SunWiz Group is doing. And the dots are easy places to see where acceleration would be applied. And so this sort of distributed architecture for a kind of video processing mixed reality experience on the way to our original application goals would really take advantage of each of those things, and we're hoping to plug them in soon. So through those two integrations, we're able to think a little bit more about how to compare or evaluate NDN as it might relate to TCP/IP, and for these types of applications, which kind of don't exist yet in many contexts. And I guess I should clarify that this data flow is all for live video, just to be clear. And then that video gets stored in the middle, and certain processes act on historical data, certain processes act on live data, certain processes act on a combination. And we do have low latency requirements, so in the kind of hundreds of milliseconds or so, from the left all the way to the right would be ideal. We're not trying to rely on things that are really, really fast, but we do have some latency requirements even in that example. So as we think about evaluating what NDN offers versus how we might approach those two types of experiences, a collaborative augmented reality experience and a kind of large-scale mixed reality experience, here are just a few dimensions that we could think about, and I'll try to dig into each one. And they're not necessarily methodically selected, but I'm going to try to methodically analyze them in a second. And then on the right, these are some of the limitations that we face in thinking about how to make this evaluation that we've been asked for and discussed with Intel. So it's difficult to figure out how we evaluate in comparison to the incumbent tools and architectures, especially in terms of performance. So we're going to need some other dimensions, and the reason I'm suggesting these other dimensions is because it's so hard to think about performance when we're comparing with these optimized stacks, especially when we have to pull those stacks apart. Research platforms are often driving us to spend a lot of effort on things that don't help with the evaluation. And the last one, I think, to some of the discussion yesterday, is the biggest wins seem to be around applications that are designed from a data center point of view. This is obvious, right? If you have an abstraction that's well supported by a certain technology platform, you should get big wins in an application designed against that abstraction. But it makes it hard to then figure out, well, how do we redesign or rethink this application that we thought of because of an ICN point of view over TCP/IP and then compare it. But I can talk a bit about that at the end, or we can get into it now. But first, to touch on performance, I think here we have an open question for the community and for Intel, which is when we look for, well, where could we evaluate performance? There are, these are 3 example categories of benefits we think already exist that motivate the application designs that we have in mind. And so we could evaluate these, or we could say there's enough literature maybe that suggests these are already benefits we're capturing in these application designs based on work in the community before. So the first is that we can take advantage of new approaches to many-to-many communication to reduce traffic. There's work that allows us to apply group encryption and even maybe fancier things like attribute-based encryption to really make not just many-to-many communication work, but encrypted and confidential many-to-many communication. We can take advantage and are trying to adjust the stack to have application nodes that grab data and even listen to interests as they see them go by, which is something that's in all advanced talks, but doesn't always make it into the code. And this is an advantage that we have in these environments. Again, to reduce traffic because a node may have seen or heard something before. There's a second category that's related to being able to forward directly on names, which is to lower the latency, lower the number of round trips to services that we need, and use those types of indirection when needed, and then maybe on the LAN, in some of our examples, not have to do that. And then finally, a kind of combination of things we can do at the consumer of the data and that the network does naturally. So the network aggregates interests and caches data, and then the consumers can just ask for the data they need. And I'll give a specific example of this in video in a second. And from this, we can also reduce traffic and lower latency. So our question about performance is, do we need to be building TCP/IP systems that parallel these NDN systems in order to evaluate these things, or are the results that are coming out of the community and suggested from the architecture sufficient? And this is something that we need to maybe hear more from. So, hear more from you about. So what I'm going to focus on, and as a way of reporting some other results from this year, are the other categories beyond performance. And these go to the soft metrics that Eve talked about and come from a framework called the Cognitive Dimensions Framework that I've talked about before and kind of returning to as we look for ways to evaluate the potential benefits of ICN. And I'll kind of summarize that as we get to the end of the talk. But first one is, can we simplify the tasks of the developers and eventually the tasks of the deployers? And some ways that we can potentially simplify that are to bring the abstraction of the application and the abstraction of the network closer, or have the stack become simpler. And to do things like offer progressive evaluation as you're building an application. And so, for example, be able to look at and examine the data that's being produced by early versions of the application in a way that's more application specific and relevant than just traffic analysis. So we're focusing some effort, or have focused some effort, on the development of new APIs and abstractions for NDN that offer opportunities to explore how do we simplify the development process, both for NDN, but in general for these kind of data-centric distributed applications. One such experiment that we've now used in these examples is called the NDN Common Name Library. And it explores the question of what if we integrate namespace design in app design and use a in-memory namespace representation as a way of working with the application's data. So a hierarchical tree, or a tree representation of a hierarchical namespace. That is what the application manipulates. This may or may not be the right abstraction, but it's an easy way that maps close to the expression the data on the network. And so one interesting observation from this, I'll give you a reference for a paper if you want to look a little bit more, but it's that the full name of an object on the NDN network represents an immutable chunk of data, packet, but the prefix represents typically an application data object of some kind. And so, for example, if we stop at different places in that name, we can find different types of objects and expose them at different places in this abstraction in a consistent way. So let's say we had an image file. If we went all the way down to the exact name of the packet that makes up that image file, it's some chunk of data that corresponds to a segment that is part of an image. But if we go up the name, it might be that, well, foo some image is actually a mutable object from the application's point of view. It's an image that updates over time. It has certain properties, one of which might be versioning. So if we go one name component down, that application might consider foo some image, some version to be an immutable version of that mutable object, expressed in a standard way using Indian name convention. So if we keep going down, we might break that image up into tiles that represent spatial areas of that immutable object. And so what we're exploring with this namespace abstraction is to be able to allow the application to stop where it wants, or the developer to stop where they want in the hierarchy, and use the same tools or the same kind of root abstraction to address the mutable object versus the immutable version versus the spatial segment versus the packet. And again, this may or may not be the most efficient way to do it, but it's a way to try to bring the distance between the network abstraction and the application abstraction closer together. So over the course of the last year, we have a more complete implementation of this in C++ and Python, some example use cases, and some experiments with integrating this approach with sync. So the basic idea being you have a name synchronization protocol, you use this abstraction or this API on as many nodes as you want. This abstraction maintains a picture of a part of the namespace, but not necessarily the data that fills it. You attach handlers to different places in that namespace hierarchy. Those handlers take care of going from application-produced object to NDN packets. And on the other end, consuming the underlying NDN packets and rebuilding the data object and having it appear at the other place in the tree. So I don't know if that's a clear description or not. Using sync to move names around, and then attaching handlers that do things like essentially serialize and deserialize the objects in the NDN format. So it's always, I think it's sort of cheating to show these kind of code examples where you've taken a common example and made it really short, but we did that anyway. And so this is an example in, you can make anything really short if the subroutines are doing the right things, right? But this is an example of a generalized object consumer using the CNN. It identifies a network face, in this case the default of the forwarder, defines a prefix of an object that is actually consisting of many sub-objects, so metadata, manifest, potentially segments, and other things. And it then essentially attaches that part of the namespace to the communication mechanism that it has. If we skip down to the end, we give it a certain application type. And we give a handler about what to do when it consumes that data, and then we simply say, we need that prefix, go look for it. And that prefix, in this case, corresponds to, again, an object that may have segment fetching and decrypting, signature verification, and all those types of handlers attached to it. And so we have some practical code, a paper in submission, and a link to a longer presentation for people that are interested in looking at this abstraction. And I'm going to skip ahead a little bit to a second example of trying to provide programmers with environments that allow them to work with the data in a simpler way. And this is a more direct application of NDN libraries to provide real-time video support in a visual programming language that we're hoping will allow us to experiment with some of the name-based addressing that I'll talk about in a second. So I'm not going to spend as much time on this other than to say this is a real-time 2D and 3D processing environment called Touch Designer. And we start with the common client libraries, and then provide support in this language for the common name library that I described earlier, this namespace-based way of working with data, and now a set of video publishing and consumption tools that unify historical and live data. So the concept of making video data available in an environment like that is to be able to start playing visually with what's suggested by this slide, which is we want to be able to name video in time, which we do already, but also in image space and in quality, and then to be able to show and address these things visually in a way that maps directly to those data formats. And so this is part of the journey of trying to not just make these things available in some declarative programming language, but also in visual programming tools that will let us look at how to play with those rivers. So this is some work from the last year, roughly exploring this idea of how can we bring simpler tools to developers that map network primitives to application programming environments. So if we kind of go a step further in talking about abstractions and the expressiveness of the abstractions, I think that'll help us to kind of return eventually to ICN, things that feel familiar as ICN principles. So this is one way of thinking about, certainly from a practical point of view in the real-time applications that we're doing, which are not, don't involve many nodes, but often small numbers of nodes. We think about video in this way. So there's a producer acquiring video and pushing it out to consumers over encrypted channels with some potential control. And there are obviously many variants of this, but the same basic idea. The consumers probably need to figure out how to store it on their own, or at least have something else happening on the other end for storage, or happening behind them for storage. This model of video, though, from an application point of view, is based on analog video from, I don't know, 60 years ago. That there are channels of video that we are transmitting in a direction, and we consume them in order. And so not only is this kind of IP-centric in a way, this is how we tend to do video streaming, right, on the network today, it's also the old model of video. And so when we talk about updating or making video more expressive by using ICN, this is actually not it's not an ICN idea. It's saying, what is video going to be like in applications now or in the future that is not video from the 1950s, and how can we take advantage of the expressiveness in NDN to make that more available to developers? So this is a data-centric way of thinking about video, right? Which we still have, for now, video frames that are produced in order. We retrieve those video frames as needed in individual consumers. And the data was, or you know, the ICN sort of canon, so the data is secured at creation, et cetera, and we can consume them in any order that we want. And so when we go back to this kind of simplified picture of video, once we get to time 2, we can issue an interest that lets us, or a set of interests, that let us pick just one rectangle from one time, or over a series of frames. We can pick which quality we want, and we do that just by expressing these properties in the name. And so by starting to apply this in actual projects, we've sort of figured out we're now thinking of video in a hybrid abstraction. So we're thinking about it as a stream, just like it used to be, as a bus that we can sort of pick from as we wish in individual consumers, sample in time. So I want just this corner of the video to play out indefinitely, or I want every keyframe only. These are just different fetching patterns, and fetched essentially from the bus, at least in our application. Or as a key value store, where there's some name and we're just fetching the key value retrieval that we need. And so this hybrid abstraction, though, is a very different way of thinking about video coming over the network, and it speaks to the benefit of NDN, which is we don't see those security containers anymore, security channels anymore, right? So by making that step from securing the channel to securing the data, we can bring the abstraction that we're using for video on the network much closer to the way we want to think about digital video today, and not based on analog video from the 1950s. So I'm going to speed up now to get to the end. We have an ICCN paper that suggests or kind of muses about how would we have built the system in TCP/IP to do the same thing. So we didn't build it, but spent a fair amount of time thinking about what would it look like if we did the same thing over TCP, or really UDP over. And from that, try to understand what are we gaining from NDN. Some of the other things that seem nice for us to find in these integrations and experiments this year were the opportunity to generalize data exchange. So in the upper left, you see a namespace design for a generalized object stream, which is basically an object that has some metadata description that looks a lot like a MIME type or an expanded MIME type, a manifest, and then the actual components of the data, plus some other information, and the main components that are needed for the RDR, the real-time data retrieval protocol that Alicia's group put together. And that's what we use to pass things like JSON messages around the network in these examples. But with some reorganization of the namespace on the right, which is the NDN RTC namespace, a more complicated namespace for video, we can align at least some of those components so that NDN RTC video data can be consumed and stored by simpler code for these generalized objects. So we have this notion of being able to generalize at least a little bit, or create a kind of hierarchical abstraction for generalized, specialized data types into more general ones at the level of what's exchanged over the network. So this is something that we might do in many different ways when we're putting a piece of software together or designing an approach to data representation and storage. But now we're actually doing that on the network as well because of what NDN allows us to do in the expression of those objects. So this is just the beginning of trying to understand namespace design, not just from an application-specific point of view, but also from a generalized tool support point of view as well. And finish with a quick suggestion of how we might structure evaluation beyond performance. And so there's existed for some time a framework introduced by T.R. Green in 1989 for the analysis, essentially, of notations. And not really a cognitive model or guidelines or a description of functionality, but just a way to have discourse around the value of different types of notation. And then he expanded that with some other authors in the 90s, in the mid-90s, to focus on the cognitive fit between mental and external representations in programming language. And so with that, that work is getting closer and closer to looking at how data is expressed, how algorithms are expressed, and in different languages, and from visual programming to all different types of text-based programming languages, and to start to come up with some dimensions to have discussion around the pros and cons of different representations in different languages. And so my suggestion is this is a place that we could look as a starting point for discussing network architectures, expressiveness, simplicity, and generally their value in these soft dimensions, these dimensions that are very important to whether we can practically use them and what the practical costs of deploying them are. So I'm happy to send the references around, or some of the work that I'm going to try to do in the next year is to adapt these a little bit more to our NDN to TCP/IP comparison, in addition, hopefully, to the quantitative comparison that other folks are doing. So our next steps, looking into the third and final year, is to flip our model a bit. So our model in the past had been, we're going to receive all the research innovations from the different groups, and then we're going to integrate them into applications. We're going to kind of flip it around and take this tool set that we have, these different libraries and examples, and provide them to the other research groups so they can build examples that are emerging from the same tools and from these application ideas, but without us becoming a bottleneck. We'll continue to look at the requirements developments for each of the groups. We are going to do an experiment, or we are currently currently doing an experiment in whether we can demonstrate spatial selectivity in video, so using a codec that supports spatial tiling and be able to express, it's a little easier than SVC, then scalable video coding, so is to express, essentially allow NPN video streams to be expressed in terms of space as well as time, or inner space as well as time. And then we're going to work with Alicia's group in terms of comparative evaluation of these different approaches to remote procedure invocation and some of the pub-sub versus sync discussion, and then try to summarize the results. That's it.
So a couple of things. One is, when I was trying to make video work well over CCN and NVN, I discovered that the encoders have already screwed you. Because they've either thrown away information because they think the receivers and the renderers are dumb and would never use it, so they eliminate it from the output stream. Or they linearize the output in both decoding and presentation time, so that you basically have to post-process everything to recover all the things that you need. Are you planning to apply some resources to go back and fix encoders so that you don't have to do all this?
I think we would like to. It's frankly just outside of the scope of what we can do from an engineering level.
You can sort of fix up the latter, but the former is really problematic. The encoders know, for example, the output quality metric of every frame, right? And they throw it away, right? And it never shows up in the output stream. So all you have is the representation.
I mean, I think if we're able to grab, it depends on where the hooks are, right? If it requires modifying the encoding pipeline, it's not going to happen. If it's data that we can grab from that, then we might.
And you don't have to change the actual encoder. It's the whole post-processing that comes out of the encoder.
Yeah, and some of the, yeah. So the answer is, if we can get there, we would love to do that.
The reason why I think this is relevant here is that in a serial session-oriented TCP-like IP environment, much of that is actually, you couldn't use it because you forced everything down a serialized presentation order type. Right? Actually, they send it a decoding order, which is even worse. So in order to demonstrate some of the benefits of the data-centric, per frame approach over TCP, you can show that, well, nobody bothered to do this with TCP because you couldn't exploit it, right? You couldn't fetch things in non-encoder specified order.
Right, and even the use just of parallel, so many of the encoders now are also, or can be parallelized in some way that we can, there's a lot that we could do. I don't know that we'll get there. A lot of it we inherit as delay. We wait until we have what we need to be able to do something on the decoding side.
And then the second question is, the way you're talking about spatial division as tiling only, doesn't that run into problem? Doesn't that sort of like not give you the information if there are multiple cameras? Don't you actually want to project the video into a coordinate system rather than simply say this is the following macro blocks of the encoded video?
Yeah, I think this is just a first pass. So that kind of the progression that we would see is this is just an example of something we think would be useful in these kind of real-time video applications, which is consumers only to select what they need. It's called, we call it vertical editing, I think. And so, right, so selecting only the part of this 8K image that your device actually needs at the time.
But you may need that part of an 8K image from two different cameras that are seeing the scene from two different angles.
So, yes, and so so the second step was then to look at maybe 360-degree video representations, which is still not quite doing what you're describing. And then there are, we have some systems to do camera alignment. And it's sort of just hitting the resource limits, not so much that we want to do.
Just one free piece of advice, don't follow the method that the people who built the multi-screen video conferencing systems did because they got the coordinate system all wrong. Okay. Right? They used Cartesian rather than polar coordinates.
Yeah, okay, I can see how that would be.
So I'll go with real quick. I like Dave's comments. I will go the second one first. I think that if I start on the levels in the front apps, fundamentally we're really talking about how you chop the data into application, recognize the label units so that we can ship them individually. That's doesn't understand that remaining open when given the application in these scenarios. But for the first one, I cannot say enough thank you for pointing out the problem. This is the thing we got into. We mentioned it in the annual report. That is, in the original solicitation, it says that, hey, we know that the current internet is TCP/IP, so we can just do edge. Can you build an edge information-centric app? And we realized it's not so much physically you can cover the edge, where you can build a ICN natively over there. There's an even bigger question. That is, the edge includes the applications. And look at all the generations, multiple generations of the application developers were educated to produce something that you can fit into a socket. So that's what the mental model is. So therefore, the all existing application packages, a lot of them are very useful, except that we cannot fit them into this data-centric then to make them work. And the ICN-WEN support doesn't really have that part of the thing to say build an information-centric application. So you can really demonstrate this ICN-WEN. I think that I just want to point out that's really the great challenge that we're battling with. We tried hard to do this integrated text. Alex and others can tell you how damn hard you try to put the security into the existing apps and totally have no sense of security. And they don't give you a kind of a handle or a nudge for you to put things in something.
One simple question is, you on one of page you mentioned not endpoint driven. What do you mean endpoint? Not endpoint driven. What is the endpoint?
I think that, okay, so that was a note on the TCP/IP kind of conceptual system diagram for the mixed reality project. So that note about an endpoint-driven concept just means, in that case, you could take even the simple example of, in this mixed reality demo application, the idea is pretty simple. Consume video from a camera, store it as it's being consumed, and do some analytics as you're storing it. And then have another process that is looking at the live video and constantly asking the stored data set, what's the closest segment of video you have to this thing that I'm seeing now? And so you can kind of a nearest neighbor search in the feature space, right? So a continuous nearest neighbor query. And so the ICN approach, and something that's reasonable to do in NDN, as we made some changes to unify live and historical video, is we don't have to distinguish between are we asking for a live frame or are we asking for a stored frame in the code. They use the same sort of strategy for development. If we were doing this in a TCP/IP setting, probably, unless we had rolled our own solution completely, we would have different chunks of the code base for retrieving stored video and handling the live streams, just because those things have kind of evolved separately in TCP/IP, especially if you're doing it in low latency context. It's a little different with Dash. So all that was saying is that we don't need to know which IP address or which DNS name am I using to go get the stored video, and if it's not local to me, how do I go onto the cloud to find it? And this kind of endpoint-driven way of thinking about where am I putting the data that's live, or where am I receiving it from, who am I sending it to, which endpoint, and where am I getting the historical video? The simplification is I'm naming the video in a way that makes sense for live and historical streaming.
Basically, you don't need to prepare the content for each edge.
that, and you don't have to manage the IP, DNS names or IP addresses of where this stuff is and the different strategies for retrieving it, which seems trivial, but when you actually deploy it is a pain.
Okay. I think the computer really comes from the fact that the whole thing, the whole thing came mainly from leveraging the ICN's pool model, basically pulling the traffic, and the pool really coming from the end. They basically requests come from the end. So it is actually, from a practical point of view, it is kind of an end-user.
Yeah. So maybe endpoint addressing driven or host centric, or it might have been a better term. Yeah.
The question is, how do you take into account when the source, when you're actually interested not in the original video source, but in some processed video source, whether it's historical or live. Let's say that all what you do, you want to put in your mixed reality my face, right? So what I need to take the original video, I need to pass it through some AI engines, probably many of them, until they realize where the face is. Take only whatever it is that my face and put it in your mixed reality, right? So it's, I know it's fairly long processing. Do you have any support for things like that when you build your ICEAR solution? Or what would be the way that we can use this system to build such solution? Because there will be such things in the middle.
And that is what's happened, even in the small demo that we have. Even in the small demo that we have here, we're consuming and then annotating and transcoding video and republishing it. So right now, that it's basically the developer keeps track of the change in namespaces, right? So there's a new prefix for annotated and republished video, and we're not necessarily particularly smart about it. I'm not sure how to give a succinct answer, except it seems like the tools are there, right? You can republish on a frame-by-frame basis, if that's the right boundary, essentially a signed manifest that tells which components to retrieve to assemble the final video. If you want to do it at the receiver side or an intermediate node, you can use names to identify the intermediate services that are performed, and we more or less do that now. The management of what those namespaces are and how you find out about them is essentially manual. So one of the things that we're talking with Lisa's group and is an open area of research is discovering the types of processing blocks that you want, or naming them using a name function networking style approach. So I'm not sure if I'm answering the question, but I think that we are constructing those processing chains already. The management of how those individual components know what to retrieve and what the names are is something that's essentially done manually, but you could see ways to automate them.
I've really enjoyed the talk and applaud your application development and deployment efforts. I also feel can relate to the pain of modifying legacy applications not quite built for an NVM like API. But I found it a little curious that it was harder to port applications designed for a socket API to NVM. Primarily because most app developers don't deal with the socket API today at all. They use higher level libraries, and most of the world is already REST or request response based. Pretty much everything has an HTTP API except maybe remote libraries dealing with large database. And even that, implementation of request response anyway. So why is that a challenging part of the report?
If that's what I implied, that wasn't quite what I meant. It was more that there's a lot of assumptions at different places in the stack that you're using IP. And I would say it's not really involving the HTTP request response protocols at all. It has more to do with, I don't know. It seems like an extended conversation that I have to think about what the examples are. But I think Dave's comment about the codec is a pretty good one. That it's not so much that it's the high-level application APIs haven't kind of gone in a request response direction that could be adapted. It's more that the underlying components are all assuming this kind of these channel-based models, or they're assuming, that in the case, it's just any number of application level details that I would say are not request response. So an interesting sidebar, and then I'll finish, is that we did an example integration of kind of an Indian API with Firebase as transport, Google Firebase, which is a key value store that's built on top of, I assume it's built on top of HTTP, but I guess I never looked. And that worked really well and really consistently, and it was sort of an interesting experiment. And so I don't think we're saying that it's hard to use or adapt HTTP or components in either direction. It's more if you want to have a data-centric, if you start with a data-centric design and you want to implement it at protocols that are essentially below HTTP, then it's hard to make comparisons. It's not so much with the REST level APIs where the comparisons are pretty direct.